Good morning, everybody. Today we will start with the units, physical quantities, and vectors. This is the first lecture of university physics for engineers and other fields of science. So what we have within that chapter, we will discuss the nature of the physics. We will discuss the experiment. We will discuss the theory. We will discuss the fundamental principles. And also we will learn the 4 steps in order to solve any physics problem. This is very important. If you follow that 4 steps, it will be very easy for you to solve the physics problem. And then we will see 3 fundamental quantities of physics. We will discuss the units we use to measure these fundamental quantities. In addition to that, we will see how to work with units and significant figures in our calculations, and we will see how to add and subtract vectors graphically and by using vector components. There are 2 methods. During that lecture, we will finish graphically vector adding and subtraction, but vector components will be discussed on Thursday, I think. In addition to that, we will see within that chapter, there are 2 ways to multiply vectors: the scalar or dot product and the vector or cross product. Okay, we will discuss all these things within that chapter. Let me tell you something here. This chapter is very important, but another important point within that chapter that you will use the knowledge learned within that chapter everywhere. In each chapter of this course, also in physics 2, everywhere you will use that information in your physics courses. In addition to that, this information, this vectors, units, will be very helpful for you for your own courses in your own department. For this reason, I strongly suggest you to concentrate on the transparencies and try to learn, or if you know, try to remember all the important topics in that chapter. Now we will discuss the nature of the physics. So what is physics? Physics is an experimental science. So we do experiments to understand the phenomena of the nature. Then we see patterns that relate to phenomena of nature. So these patterns, what is pattern? You can consider like models, okay, to understand the phenomena of the nature. So these patterns are called physical theories. So you do experiment and then you develop a model, and this model is called as physical theory. But if these physical theories are very well established or widely used, then they are called as physical law or principle. In order to be physical law or principle, each theory must be very well established and it must be widely used. Okay, this is very important. Here, one example to the experiments. This is Leaning Tower of Pisa, you know, very famous. And this is a church just in the adjacent of this Leaning Tower. So according to the legend, Galileo investigated falling objects. So let's consider that Galileo staying here, and then he dropped some objects, and then he investigated falling objects by dropping them from this tower. In addition to that, within that church, that cathedral, let's say, there is a swinging chandelier. Swinging chandelier means sallanan avize within that church, and he studied pendulum motion. What is pendulum? Pendulum is sarkaç. You can consider like this. This is pendulum motion. He did experiments, and then he put some theories to explain that experiment. But in order to have physical law or principle, these theories must be very well established and must be widely used. Another example to the physical experiments in our country, in our culture, let's say, this is a picture from Takuyuddin Observatory. It was in Istanbul. Okay, you see many guys here, and they are very good astronomers, and they were measuring something in that time, so doing experiments. And here you see a picture of a medrese from Mardin. As much as I remember, the name is Kasımiye Medresesi. I think from Artuklu and Akkoyunlu times. This style is mainly Selçuklu medrese style. In many Selçuklu medreses, you can find such water pools. So do you know what is the aim of this pool? There is nothing on top of that pool. So during the night, this pool behaves like a perfect mirror, okay? Then you can see the stars and the position of the planets on the surface of that pool, so you can measure the distance between the stars, you can measure the distance between the planets, okay? So you can do experiment. This was very old method in astronomy experiments. Now we have Planck spacecraft. This is designed to study the faint electromagnetic radiation. What is faint electromagnetic radiation? Uzak, sönük. So left over from Big Bang 13.8 billion years ago. So we would like to investigate electromagnetic radiation. So what do you see here? There is a perfect mirror. You see, this is perfect mirror of the spacecraft. Perfect mirror here, okay? Just 1,000 years ago, and perfect mirror of the spacecraft. And here you see technicians, and here you see the reflection of these guys here. You send this spacecraft to the space and you collect the electromagnetic radiation. So method is, the idea is same. Light, electromagnetic radiation comes from space to the surface of this perfect mirror, okay? So the mechanism is same. Here, another type of experiment, very new one. This is an astronaut. This is International Space Station. This is Earth. And this International Space Station, ISS, is traveling around the Earth. And there are physicists, there are technicians within that ISS, and they are doing experiments. Okay, for example, this guy is outside of the ISS and repairing something. Physicists are doing experiments. Now, let me discuss the solving problems in physics. We have a problem and we would like to solve it. There are 4 important steps. Here, we shortly call it IC. Now, I will explain each step. The first one is identify. The second one is setup. The third one is execute. Last one is evaluate. So, for example, you have problem in this book or somewhere in another book. So, how to solve? First of all, identify the relevant concepts, target variables, and known quantities. What do you have within the problem? First of all, identify them and then set up the problem. So choose the equation. In order to solve that problem, which equation can help you? Just set up this one and then draw a sketch of the situation. This is the setup step of the problem solving strategies. And the third step is execute the solution. So this step is completely related to the mathematics, okay? So this first and second step are related to the physics, and this step where you do the math. Then finally evaluate your answer, whether your result is meaningful or not, okay? You have to compare your answer with your estimates. This is very important step. Sometimes you can get very bad result and they can be meaningless, okay? So you have to evaluate your answer. You have to evaluate your solution. This is very important. And if you check the examples within the book in Young and Freedman, you will see that each problem solved, each example solved with that method, IC, okay? Identify, set up, execute, evaluate. I will show you one example within the transparencies. Then let me continue with the idealized model. We are physicists, and sometimes problems may be very, very complicated, okay? So then we have to simplify the problem in order to analyze them. So here I will show you one example for the idealized model. This is real baseball in flight, okay? It is flying like this. This is baseball. But how to idealize this one? This is the idealized model of the baseball. So in real case, baseball has some volume, okay? And it has some certain direction. And there is a gravitational force on ball. Of course, it depends on the altitude. And this is the direction of the motion of the baseball. Since there is a volume of the baseball, there is air resistance and wind exerts forces on the ball, right? But in idealized model of the baseball, there is no air resistance. We have just point, a particle. So we treat the baseball as a point object, as a particle, okay? So then there is no air resistance. We omit the air resistance in the idealized model. This is the direction of the motion. This is again gravitational force on ball, and it is constant, okay? So here, gravitational force depends on altitude. Look at this one. Here, there is a mass of this part of baseball. There is a mass of this part of baseball. So distance from the ground to that part, distance from the ground to that part are different, okay? But here, if you have a single object, point object or particle, then the distance from the particle to the ground is constant. So gravitational force is constant. So in real case, the problem is complicated to solve it. In idealized models, you can solve the problem much easier. Do you have any question here in that part? And let me continue with the standards and units. We have three fundamental quantities of physics, which are length, time, and mass. And their units of these standards are defined by international system, SI, very famous name. So length has unit of meters, time has unit in seconds, mass has unit in kilograms, okay? There is another unit system, CGS, in Turkish CGS, okay? Instead of meters, centimeter, instead of second, again second, and instead of kilogram, we use gram for the mass, okay, in CGS unit system. But there is another unit system, the British system. So in the British system, they use inch, okay? Especially in engineering, inch is very important. It is widely used. So 1 inch is equal to 2.54 centimeter. And for the force, instead of newtons, in the British system, pound is used, and it is equal to that number. And you know, mile, this is very important also in navigation, okay? 1 mile is equal to 1.6 kilometer roughly. This is a speedometer from a United States built automobile. What do you see here? There are two scales, mile per hour and kilometers per hour. Mile is used in the United States and in some countries. So now let's come to the standards and units. So length, time, and mass. What is the standard length? What is the standard time? What is the standard mass? So what is 1 meter? What is 1 second? Who defined them? So this is very important question. The 1 second is defined with the frequency of microwave radiation. This is necessary to excite cesium atom. Here, there is a cesium atom, okay? This is the electron within the cesium atom, and microwave radiation, electromagnetic radiation, with a frequency of exactly this cycles per second comes to the cesium atom, and then it causes the outermost electron of a cesium atom to reverse its spin direction. Okay, so atomic clock uses this phenomenon to tune microwaves to this exact frequency. So 1 second is defined as the time required for this number of cycles of this microwave radiation, frequency of that electromagnetic radiation. It is started from 1967, okay? Until 1967, in order to define the time, we used average time between successive arrivals of the sun at its highest point in the sky, okay? So from 1889 until 1967, we used the sun. But now we are using much accurate standard, which is used in atomic clocks. This is the standard for the time, and standard for the length. So what is 1 meter? 1 meter is defined with the distance that light travels in vacuum in 1/, the second. Light travels exactly 300,000 kilometers in 1 second. So this is the measuring the meter. And what about the standard of the mass? Until 2019, until the last year, the standard of mass, the kilogram, is defined with the mass of a particular cylinder of platinum iridium alloy. Here you see a cylindrical shape of platinum iridium alloy, like battery, you can see, okay, but pure platinum iridium alloy. It is 1 kilogram. But it changed in 2018. Now the kilogram is defined in terms of 3 fundamental physical constants. Speed of light, remember that speed of light gives us the standard of the meter, and frequency of cesium atom. Frequency of cesium atom gives us standard of the second for the time, and we have Planck constant. So these 3 important fundamental physical constants now gives us the standard of the kilogram, starting from 2019. In the book, you will see that the standard is defined with that one, but it is not updated. So this is the up-to-date information. Do you have any question here in that point? I have 3 transparencies, and then I will have a short break. Okay. So now let's discuss the unit prefixes. Prefixes means ön ek. Here, micrometer, it is prefix. This is meter, prefix, milligram, prefix, kilogram, prefix, okay, gram, nanosecond, second. So you can convert 1 micrometer to the meter, okay? This is the size of some bacteria and living cells. 1 kilometer can be converted to the meter, okay? And 1 milligram can be converted to the kilogram. 1 gram can be converted to the kilogram. 1 nanosecond can be converted to the second, 10 to minus 9 seconds. So here I have already discussed the British system. Now let me give you some typical lengths in the universe. So this is the limit of the observable universe, 10 to power 26 meter. And this is the distance to the sun, 10 to power 11 meter. And this is the diameter of the Earth, 10 to 7 meter, 1 meter, 2 meters, human dimensions. And now here we have 10 to minus 5 meter or 5 microns, diameter of a red blood cell. And if you go further, we have 10 to minus 10 meter. This is almost 1 angstrom, okay? Smaller than 1 nanometer. 1 nanometer is 10 to minus 9 meter. 10 to minus 10 meter is 1 angstrom. This is more or less radius of an atom, okay? 1 angstrom, 2 angstrom, 2.5 angstrom. This is the radius of an atom. And if you go further, 10 to minus 14 or 10 to minus 15 meter, which is shortly called as 1 Fermi, radius of an atomic nucleus, okay? There are protons and neutrons here. Here we have blood cells. The size is around 5 microns. You can see these images by using microscopes, optical microscopes. But what about the atoms? You cannot see atoms by using optical microscope. In order to see atoms, you have to use scanning tunneling microscope or transmission electron microscopy. We have to use electron microscopies. So let me continue with the unit consistency and conversion. First of all, let me choose the laser pointer. This part is very important when you are solving the questions, okay? So students usually do some errors and mistakes within the calculations. This sometimes comes from the unit inconsistency and errors in the conversions. So you must be very careful. Be sure you are adding apples to apples. This is very important. And the terms to be added or equated must always have the same units. So always carry units through calculations. So for example, you are carrying out a calculation, always use units. Okay, for example, here we have a question. If a body moving with constant speed v travels a distance d in a time t, these quantities are related by the equation here. The distance is given by velocity times time, right? So the unit of the distance, meter. What about the unit of the velocity? Meter per second, right? What about the unit of the time? Second. So always use units within the calculations. For example, let's consider that distance is 10 meter and time is 5 seconds and velocity is 2 meter per second. So if you put the units here, so what you will see, this second comes from the time, we'll cancel this second, then we will have meter here. On the left side, we also have meter, okay? An equation must be dimensionally consistent. Meter, meter. If you are second on the left side, you should have second on the right side. If you have joule on the left side, you should have joule on the right side. Okay, don't forget this. So if you use the units within your calculations, you will get much correct results, okay? Another important thing is that conversion. So for example, here we have 3 minutes and we would like to convert this 3 minutes to the seconds. So how to convert this one? So during conversions, you must be very, very careful. 1 minute is equal to 60 seconds. So put it here. This minute will cancel this minute and we will have second here. 60 times 3, we will have 180 seconds. So we converted minute to the second, okay? This is the unit for the time. This is unit for the time. So we have unit consistency, okay? So these things are very important in your calculations. Sometimes students, especially students in the first year of the university, usually do not care about these units and conversions. Just multiply 3 with 60, okay? Then just write 180 without any unit, or just put 3 without any unit. So if you do these things in your university courses, you can get bad results or errors in your calculations. For this reason, I strongly suggest you always carry units in your calculations. Any question here in that part? Okay, then let's discuss the uncertainty in your calculations and significant figures. Uncertainty means belirsizlik in Turkish or error, hata payı. What is the opposite term for the uncertainty? Accuracy, kesinlik. Okay, so What about the significant figures? Significant figures means that in Turkish anlamlı sonuçlar, or in English meaningful digits, anlamlı sayılar. Okay, so I will give you some example. Here we have a cover of book, for example, and we would like to measure the thickness of this cover. Okay, I would like to measure the thickness of that cover, and this thickness is 2.91 millimeter. So 2.91 millimeter. We are talking about 2 millimeter, and we are giving additional 2 digits here, 91 millimeter, 0.01 millimeter. So you say that accuracy is given by 3 digits, 291. So we have 3 significant figures. Okay, with this we mean that the first 2 digits are known to be correct. So this one, 2.9 millimeter, while the third digit is uncertain. Okay, so the accuracy of the third digit is not so good as this one's. So the last digit is in the hundredths place, so the uncertainty is about 0.01 millimeter. With hand, it is not so easy to accurately measure this last digit. Now, another important point, for example, 2 values with the same number of significant figures may have different uncertainties. So here we have 1, 2, 3 digits, so 3 significant figures. Okay, here look at this one. We are talking about a distance given as 137 kilometer. 1, 2, 3 significant figures. Okay, 3 significant figures here, 3 significant figures here. Here the uncertainty is about 0.01 millimeter, but here the uncertainty is about 1 kilometer. So instead of 137, you can measure 136 or 138. Okay, we have 1 kilometer uncertainty, but here uncertainty is about 0.01 millimeter. The last point here with the significant figures, distance given by 0.25 kilometer has 2 significant figures. Here you can say that there are 3 numbers, but 0 to the left of the decimal point does not count. Okay, if you have 0 here, you don't count this one. Here we have 1 and 2 significant figures. Okay, so if this number is given by 0.250, then we have 3 significant figures. Okay, uncertainty is given by 0.001. Here uncertainty is 0.01. Okay, so these are the uncertainty and significant figures, very important in calculations. I will give you some more examples. So how to use significant figures? For example, you are doing multiplication or division. So look at this one. Here, just concentrate this transparency. Here we have a number with 3 digits after point. Okay, so significant figures 3. So here significant figure 2. Here significant figure. Here I can measure precisely. Here I can measure precisely 3 digits after the comma, but here I cannot measure precisely. 2.2. Okay, uncertainty is 0.1. So the result here, I mean in terms of significant figures, must be like this. The result can have no more significant figures than the factor with the fewest significant figures. Here on the left side, this number has the fewest significant figures. Significant figures are 2. On the right side, result can have only 2 significant figures. So here we have 1, 2 significant figures. Okay, so the fewest accuracy on the left side defines your accuracy on the right side. So again here, for example, in multiplication, So here we have 1, 2, 3, 4, 5, 6 significant figures. Here we have 3 significant figures, and result, look at the result, it can be 3 significant figures. You cannot give 6 significant figures on the right side because here we have only 3 significant figures. Is this part clear? If not, please let me know. Now let's continue with the addition or subtraction. For example, here we have this number plus this number minus this number, and we will have result. So look at this one. After the decimal point here, we have just single number, you see, just 0.2. But here, after the decimal point, we have 1, 1, 5, 3, 3 numbers, 3 digits after the decimal points. Here, 1 digit after the decimal points, and here 2 digits after the decimal point. And the result can have only 1 digit after the decimal point due to this number with the largest uncertainty. This has better accuracy than this one, and this has better accuracy than this one. So this result can have accuracy as this guy, okay? Is it clear? So what about the uncertainty or errors or accuracy in calculations and significant figures? They are very important in calculations. Here, there is one example from old times. This is train station, okay? And this is a train. So as this train mishap illustrates, even a small % error can have spectacular results. Maybe you have watched the Dragon Crew flight to the International Space Station during this summer. You know, SpaceX company sent 2 astronauts to the International Space Station by using Dragon Crew, right? Dragon capsule. So this Dragon capsule went to the space and then connected to the International Space Station. So uncertainty is very, very important. Even very small % error can have spectacular results in technology. Okay, for example, we can consider guns or fighting jets or unmanned armored vehicles, for example. You shoot somewhere or you send a missile to somewhere. Let me draw here. Here, there is a missile station, and there is a radar on top of it. And here there is an enemy, okay? You have to hit that target, and then you send a missile. So missile should hit that point, okay? Is it clear? So missile should hit that point. And let's consider that here there are your friends and you mustn't hit them. So in that case, let's say the distance is 1 kilometer, for example. So even a small % error can have spectacular results, okay? Sometimes these guns, these missiles can hit some civilian places, okay? So this is very important for many fields of science and engineering and many fields of life. Okay, so let's continue with the vectors and scalars. Scalar quantity can be described by a single number, just magnitude. For example, temperature. For example, energy, okay? We are talking about temperature plus 5 degrees or now plus 30 degrees Celsius or minus 20 degrees Celsius, okay? Just numbers, just magnitude and unit, but it has no direction, okay? Scalar quantity has no direction. It has just number, just magnitude. However, a vector quantity has both a magnitude and a direction in space. Again, let's have a look at example. This guy is walking on a wintry day, okay? The outside temperature is, let's say, minus 20 degrees Celsius, and this temperature is scalar, and there is a wind in that direction, okay? So the magnitude of the wind is written here, 15 kilometers per hour. And what about its direction? It comes from the west, okay? A vector has some certain direction, okay? So this is very important difference between scalar quantity and vector quantity. This is given by just a magnitude, and this is given by both a magnitude and direction in space. So within the book, Young and Freedman, and also within the lecture notes, transparencies in that course, we will use a vector quantity which is presented in bold face italic, bold with an arrow over it. You see this arrow here. And the magnitude of this vector is shown by italic without arrow or with this symbol. We use magnitude, okay? This is vector, this is magnitude. This is vector, this is magnitude, okay? Don't forget this one. So this is the main difference between scalar and vector. So force, for example, vector. Momentum is vector, okay? Temperature is scalar. Energy is scalar. So you will see many vector quantities. We will discuss them later on. Let's discuss the displacement, very important term in physics, especially for physics 1. Displacement is a change in the position of an object. In Turkish, yer değiştirme. Here, look at this one. This is the position 1, initial position or starting position or first position. And this is the position 2, ending position or second position or last position, you can say. So you move from that point to that point. And this is the displacement. And displacement is a vector, okay? Displacement is a vector, don't forget. It has magnitude. For example, the distance is 1 kilometer, let's say, and it has certain direction. Magnitude, 1 kilometer, direction is this one. So this is the displacement. Another representation of the displacement, this is the first position. This is very important, listen carefully. This is the first position and you move like this, okay? And then finally your last position. What about your displacement? This is not the displacement. Displacement is this one, okay? You change your position from this place to this place. This is the displacement. So displacement does not depend on the path taken, even if the path is curved, it doesn't matter. So now let's have a look this one. This is the first position and you follow this path and finally you come to that point. So first point and second point or last point are same. So total displacement is 0, okay? Displacement is 0 in that case. Now how to draw the vectors? We draw vector as a line with an arrowhead at its tip. So this is the vector. This is the arrowhead. Okun başı, ok başı gibi. This is tail, kuyruk in Turkish. This is head, baş. Okay, don't forget this one. Head, tail, tail, head. So the length of the line shows the vector's magnitude. This length shows the magnitude and the direction of the line shows the vector's direction. Direction is this one. So here we have displacement A and we have another displacement which is shown by A prime, okay? Since its direction is same, since its magnitude is same, this second displacement is equal to the first displacement, okay? So if any vectors have equal magnitude and same direction, they are equal. Okay, don't forget this one. So what we have here, magnitude is same, like this one and this one, but the direction is opposite, okay? Since the direction is opposite, this new vector B is equal to minus A. They have same magnitude, but direction is opposite. This minus here shows the opposite direction. Any question here? Then let me continue. How to add two vectors graphically. We can add two vectors by placing them head to tail. So look at this one vector. This is the head of the A vector, and I have another vector which is given by B, and I would like to add them to each other. So put the tail of B to the head of A, head to tail, okay? Then draw the resultant vector C, A plus B, okay? So you can add them also in reverse order. For example, here we put the B to the head of the A, but here we will put A to the head of B. Again, head to tail, head of B, tail of A, head to tail method. And again, the resultant C vector is given by B plus A, and B plus A is equal to A plus B, because this blue vector and this blue vector have same magnitude and same direction. For this reason, A plus B is equal to B plus. The order doesn't matter in vector addition. We can add two vectors by placing them tail to tail and constructing a parallelogram like this one. Here I have A vector, here we have B vector, okay, tail of A, tail of B, okay, we add them tail to tail, and here you can draw a parallelogram for A and B vectors, okay. So in general, what do you see here? Take this A vector and carry this vector here, okay. Again, let me draw, maybe you will better understand. I will draw the A vector. Okay, so what do you see here? This is the head of the B vector. This is the tail of A vector. Again, head to tail method, and we have resultant C vector. What happens if they are parallel and anti-parallel? We will discuss these conditions. If they are parallel to each other, like this one, let me choose again the laser pointer. Here I have A vector, B vector, and A plus B gives us the C resultant vector. If they are anti-parallel, for example, here I have A vector in that direction, it has certain magnitude, and this is the B vector. It has certain magnitude, but its direction is opposite to the A, and the resultant C vector is given by A plus B. So A plus B is this one, okay? So actually, magnitude of C is given by A minus B. So now let's consider that we have many vectors, more than two vectors, and how to add this many vectors graphically. So to find the sum of these three vectors, here I have A vector, B vector, C vector. They have different magnitudes and they have different directions. So you can add them in any order, it doesn't matter. So you can do like this, A and B head to tail, and then resultant is D, then C plus D. D is the resultant of A plus B and plus C, so this is the resultant vector. This is one method, or you can do like this, A, B head to tail, and B, C head to tail. So this is the resultant vector, okay? Or you can do like this, B plus A plus C, head to tail, head to tail. So this is the resultant vector. So you can add more than two vectors graphically with that methods. Do you have any question here in that part? I will continue with the subtracting vectors. Here we have vector, and here we have B vector, okay? So A minus B will give us A plus minus B. You will see that. So what was the minus sign here? Minus sign is showing us that the opposite direction. This is the B vector. Minus B has same magnitude with that one, only its magnitude is opposite, okay? So now let's do that. Here on the left side, I have A vector, you see, A vector, and B vector here, put B vector here. So this is A minus B, okay? So look at the right side. I have A vector here, and we have B vector here. So this is the, but this is plus, this is minus. In case of minus, look at this one. In case of minus, we add them head to head. In case of plus, we add them head to tail. Okay, here we have A vector, here we have B vector, put A here, put B here, head to tail, and this is the resultant vector, A plus minus B. Here, A vector and B vector, we are doing subtracting. For this reason, we have to combine them head to head, and then resultant vector is this one. So what you see here, A plus minus B equal to A minus B. So because resultant vectors have same magnitude and same direction. So now another important property of the vectors, and then I will finish with that example. Our lecture will be finished. So multiplying a vector by a scalar. For example, you have A vector, and you would like to multiply this A vector with a scalar number, for example, 1 or 2 or 3 or 1.5, okay? So magnitude will be number times magnitude of the vector, and the direction will not change if it is positive number, okay? So here we have A vector, and I multiply this A vector with 2, then the magnitude is twice as long as A, okay? But the direction is same. If you multiply this vector by a negative scalar number, for example, we multiply this A vector with minus 3, first of all, the magnitude will be 3 times bigger or longer, okay? This is 3 times longer compared to the A vector, but its direction is changed due to the negative number here. This is the multiplying a vector by a scalar number. Then I will finish my lecture with that example. Here, let's consider that a cross-country skier, arazi kayakçısı, dağ kayakçısı, cross-country skier. So this is river, and then this is the position of the skier. Skier, first of all, starts from that point, and then she goes 1 kilometer. This is the north, south, east, west, 1 kilometer along the north. And then it goes over bridge here, over the river, 2 kilometer to the east, okay? So this is the resultant displacement. So the result will be more than 2 kilometer. The result will be more than 1 kilometer, and the result will be less than 3 kilometers. Okay, you can estimate this one without any calculation. So how to calculate magnitude of this displacement and how to calculate the angle here. In order to calculate magnitude and its direction, we have to use trigonometry. Okay, you already know this information from your high school years, and by using that information, we will calculate the magnitude of the resultant displacement, and also we will find its direction. Look at the sign here. This is the east, this is the north, and this displacement is something like this, okay, between east and north, right? So, but which angle between east and this resultant vector, or which angle between north and this resultant vector, you can calculate this one. The distance from starting point to the ending point is equal to the length of the hypotenuse. Actually, this is hypotenuse, right? So you can calculate 1 kilometer square plus 2 kilometers square is equal to displacement square. Okay, so you can calculate 2.24 kilometer. This is the magnitude of the resultant displacement. So what about the phi angle? I mean the direction of this vector, displacement vector. You can calculate tangent phi. Phi is here. Tangent phi can be calculated opposite side over adjacent side. Okay, so look at the calculation. I am using the units. You see, units are here, 2 kilometer, 1 kilometer. So the result is unitless because kilometer cancel this kilometer. So the result is 2. Tangent, if tangent phi is equal to 2, then phi is 63.4 degrees. You can do it by calculator. So then we can describe the direction of this resultant vector 63.4 degrees east of north. Okay, so this is the north. So vector is like this, 63.4 degrees east of north. Or you can consider like this, just complete 90 degrees here, then this angle here between east and this resultant vector will be 26.6. Okay, so this is the addition of two vectors at right angles. Do you know what is right angle? Right angle 90 derece demek, dik açılı demek. Next, we have components of a vector, but here I will stop and then we will continue on Thursday to discuss the components of a vector. If you have any questions, please let me know.
Hocam en sonunda yine bir şey gösterdiniz ya, orası yine görünmedi.
Okay, maybe you are talking about right angles. Right angles means 90 derece açılı veya dik açılı. If you have two vectors at right angles, you can add these two vectors with that method, as I explained here, and you can calculate the direction of the resultant displacement vector. Between east and north, you can get the angles here. Maybe you mentioned this one, but I don't know. If you can tell me in detail, I can repeat.
Evet hocam, anladım şu an, orasıydı.